Okay, so back to the presentation on linked data structures. Our conversation last week was about the possibility of having a linked list, which looks like this, right? The data structure which really kind of links to itself. So we have individual nodes, and they know about each other's existence. And simply by using C++ pointer, if we can link them together, then we can have this. Now, I don't know if I mentioned the importance of linked list. Linked list happens to be an alternative to an array. Array actually is very much preferred to a linked list because array is faster and its memory can be managed better. If, for example, we use dynamic array, which is yet to come in our conversations in this class, then it's a better choice performance-wise. But a linked list truly becomes a foundation for building other types of data structures, networks or trees, for example, right? So if you can take this as a building block, you can essentially, if you create a node which could be pointing to other nodes and kind of fork or split into multiple branches, then you can build a tree. But still, in a tree, a list is a building block, right? So to demonstrate, we probably need this anyway. Little drawing is that if you picture a tree which maybe looks like this, then looks like this, then maybe there are some branches that are coming out different ways, something like that. So if we invented a node that would contain could provide multiple branches, then you can branch and create a tree. But still, in many cases, the regular list continues to be part of the tree, right? So somewhere here I may have another split to multiple branches, right? But somewhere in the middle, right here, I only have a regular list. So a list is a building block for those kinds of things. Now, trees are extremely important. The trees help us to build configuration files. As you know, for example, Windows registry is entirely hierarchical data structure. Other examples of that would be on the database side. You hear a lot about relational databases. So relational database is basically a configuration of multiple tables which refer to records from one table to another table. But at the same time, what makes that database fast is an index. There is typically an index file or index structure within the database file, which basically provides quick access. So if there is a table of some sort inside, if this was the database, it's possible that some of these things actually refer to particular records. And if you traverse this table sequentially, like from here to here, top down, to get to this record, it can be very slow. But if you use index, the database optimization engine essentially jumps to this record almost in real time. So those things are extremely important. So trees and of course lists are very, very important data structure that basically become a design building block. So let's go to the stuff we started covering. We decided to maybe cover a node, the node class. So if we could design this one individual element right here, the node, which all that it can do in our case is be able to point and link with another node. So if you have two nodes, you can create them independently, but then you can tell this node to link to this one, right? And if that's possible, then you can also tell this one to link to another one. Do something like this, and you can formulate the list. Or you can then create another node right here and tell this node to link with it, or rather, not just link with it, but also insert it in front. And in that case, we'll take the eraser, temporarily get rid of this link, and instead, what we'd like to have is that this one will be pointing here, and this one will be pointing down here, and so we can insert things. We can also remove things. Obviously, if you get rid of this one, then this node should be pointing directly to this. And we also said that the end of the list, if this is like a singly linked list like this, then we would like to distinguish two ends of it. So this would be pointing to nothing, like have a null pointer at the end, telling us specifically that there's nothing else beyond this node, so we know where the tail is. And we should also give somewhat special recognition to the first node, because this is the one that gives us access to the rest of the list, right? Because the links pointing in one direction in a singular linked list, which we're trying to examine right now, if you only have access to this node, you lost the beginning of the list. There is no way to jump in this direction. You always have to start with the root or the head of your list. So some special recognition to some of the nodes, but it all can be constructed, manipulated, and so forth. So this is where we'd like to pick it up and say, how about we design a class, we will name it a node, and this node, what can it do? Well, it will be obviously having a pointer to the next node, right? So if we kind of like clear this up, right, and try to think about it, the node that we're trying to design right here will have the structure in memory. If I try to picture this object in memory, that it's already created and allocate some space in memory, then it will contain this pointer to another node. So this will be our pointer P next, right? So this is a pointer to another node. So if I kind of clone this, if I just take Control-C, Control-V, if I have another node, what it's desirable when the list is formed, then this pointer should be pointing to this next object, right? Because each object in memory has memory address. It's perfect to have a pointer which points to the next one. And of course, this one, if this is the end of the list, then it should be a null pointer, and we will use just a little box with an X to specify a null pointer. All right, so something like that. So we'd like to, and so now if we design the single node, and if we can instantiate multiple copies of them, then presumably we can make a list out of these individual boxes. Well, clearly, in addition to this, once we have the structure working, then the node can grow in terms of how much other useful data could be stored here, right? In a node, you can store like person's name, telephone number, social security number, and something else, right? So you can each node then can grow, besides its list function, each node could accommodate some data, and that's useful. We call it a payload, or the value of the node, right? But for now, we're not focusing a lot on the data aspect. Mostly, we're going to be focusing on functions which allow us to create, manipulate those lists. All right, so that's the idea. So the proposition is to have this node, and I think maybe I have started this project. Let me save